Okay, section 9.5 is testing convergence and testing convergence at endpoints. As I said, we're going to look at several tests. This is just really to get stuff down into your notes and to see it the first time. We'll be working on these in class together. So the first test we're going to look at is the integral test. Remember, so far you have the nth term test. You know how to find whether a geometric series converges or not. We have the ratio test. We did a comparison test. So we're continuing on with other tests. The integral test. Let the set of a sub n be a sequence of positive terms. Suppose that a sub n equals a function in terms of n where f is continuous, positive, decreasing of x for all x greater than or equal to n, a positive integer. Then the series from n to infinity of a sub n and the integral from n to infinity of f of x dx, in other words, or f of n dn, if I compare them, either both of them will converge or both will diverge. So in other words, if I can integrate the a sub n term and prove that it converges, then I can say that the sequence also converges. Let's look at one of these. So, does this converge? The integral test applies because this function, the same as my a sub n term, is continuous, positive, decreasing function for all of x, x greater than or equal to 1. That's the value I'm looking at here. So as long as those three things are true for x greater than 1, I can integrate. So I'm going to do the integral from 1 to infinity, which requires a limit. This is an improper integral. So they've rewritten this function as x to the negative 3 halves, taking the limit as k approaches infinity of the integral from 1 to k. We get the limit as k approaches infinity of this value, which is 2. The integral therefore converges, so the series converges. So it's like a comparison test, but we're integrating to compare. All right, the harmonic series, or p series. 1 over n to the p is called a p series, where p is a real constant. A harmonic series is a specific p series when p is 1. So the sum as n goes from 1 to infinity of 1 over n is the harmonic series. The harmonic series diverges. A p series will converge if p is greater than 1, and it will diverge if p is less than or equal to 1. Note that this is similar to our geometric, except it's the opposite. In geometric, if the ratio is less than 1, it converges. Here, if p is greater than 1, it converges. Okay, so we need to know this about a p series. The harmonic series is where p equals 1, so clearly that diverges. The limit comparison test. The limit comparison test. Suppose that a sub n is greater than 0 and b sub n is greater than 0 for all n. So this is kind of like our other comparison test, but instead of comparing the terms, we're going to compare the limits. So if the limit of a sub n over b sub n equals c, and if c is between 0 and infinity, positive, then the sum of a sub n and the sum of b sub n either both converge or both diverge. So again, I'm comparing one to another. So again, if the a sub n over b sub n equals 0, and if the b converges, then a also converges. If the limit of the ratio goes to infinity and b diverges, then a will also diverge. Note that if this limit equals 0 and b diverges, we cannot say anything about a. It has to be these two scenarios specifically. Okay, so let's do an example of this. I hope you're pausing and writing. Determine whether the series converges or diverges. This is our initial series. For n very large, and look at what they've done, it behaves like 2n over n squared, which is 2 over n. So I'm going to compare the terms 1 over n of the sum of 1 over n. So that's this one. So I'm going to take my original and compare it to this. So a sub n over b sub n. My a sub n term divided by my b sub n, and then simplified. As n approaches infinity, this approaches 2. So since the limit is positive, let's go back to this. Since the limit is positive and the sum of 1 over n diverges, this is my harmonic, therefore this also diverges. Okay? Alternating series. So here is a series that has that minus 1 to the n plus 1, where it flip-flops, plus, minus, plus, minus, plus, minus. These kinds of series converge if all three of the following conditions are satisfied. Each u sub n is positive. That's not counting the alternating piece in the middle. As long as each of these is positive, and u sub n is greater than u sub n plus 1, in other words, the terms are getting smaller, and if the limit as n approaches infinity, the nth term approaches 0, then it converges. So this is like taking the nth term to the next limit. If the nth term approaches 0, remember that was not conclusive for all functions, but if each term is also getting smaller, and if they are flip-flopping, plus, minus, then we can say that it converges. The alternating series estimation theorem. Again, an alternating series, if this satisfies the conditions we had previously, then the truncation error for the nth partial sum is less than the next term and has the same sign as the first unused term. Jot that down. We're going to talk about these more as we go. I don't want to do a whole lot of examples until we get into some of this. All right, rearrangement of absolutely convergent series. If the sum of a sub n converges absolutely, and if b sub 1, b sub 2, up to b sub n is any rearrangement of the sequence, then b sub n also converges absolutely. So in other words, if I have a sequence but I rearrange it, that still does not change its convergence. Okay. Same thing but with conditionally. If a sub n converges conditionally, then the terms can be arranged to form a divergent series. So it works for absolute convergence, this does, but not necessarily for conditionally convergent. How to test a power series for convergence. So these are the steps you're going to go through when you see a power series. 1, use the ratio test, or find the values of x for which the series converges absolutely. In some instances, the series converges for all x. In rare cases, only at a particular point. So use the ratio test to find an interval of convergence. If the interval of absolute convergence is finite, test for convergence or divergence at each endpoint. We have not paid much attention to endpoints before. We are now going to. The ratio test fails at these points. That should say if. Use a comparison test, the integral test, or alternating series test. If the interval of absolute convergence is this again, conclude that the series diverges for the absolute value, because for those values of x, the nth term does not approach 0. Just write Don't worry too much. Get this down in some form so that we can use it as we move through these tests. So here's an example of finding an interval of convergence. The previous tests were just to tell whether they converge or diverge. Now we're looking at our interval again. For what values of x does the following series converge? So here's my series. I'm going to apply the ratio test to find the interval of absolute convergence, then check the endpoints. So here's our ratio test. This simplifies down to x squared. The series converges absolutely for x squared less than 1 or the interval -1 to 1. The question is, what happens at those endpoints? At x equals 1 and x equals -1, the series is this. This converges by the alternating series test. So I can say that -1 and 1 are included in my interval of convergence. The top of here, I know it's cut off, it says procedure for determining convergence. This chart is going to come in very, very handy. First thing we're going to try is the nth term test. Is the limit of a sub n 0? If yes, or if we're not sure, we're going to go on to other tests. If no, we say it diverges and we're done. We then look for any of these tests. The geometric series is the first one I would look for. So if it is a geometric series, then we can know that it converges to a over 1 minus r if r is less than 1, and it diverges if r is greater than 1. So if it is a geometric series, we can use our regular geometric information using r. If it's not geometric, we're going to see if it's a p-series. If it's a p-series, it converges if p is greater than 1, diverges if p is less than or equal to 1. If it's not a p-series, non-negative terms and or absolute convergence. So does the absolute value converge? Use a comparison test, integral test, ratio test, or nth root. If the absolute value converges, then the original series converges. If it doesn't, or if we're not sure, we're going to look at the alternating series. If it's alternating and follows all three restrictions, then yes, we can find a convergence for it. If not, look at partial sums, more advanced books. In other words, if it doesn't, we're not going to find it. Okay? So, again, I'm sorry, I should have finished off this one. Is there an integer such that we can find an interval? If yes, then we can use our convergence. If not, again, we're done. Most of the time, your things will stop here. There will not be any that require this piece, but that's the bigger picture for later on. So this is going to come in handy. We want to begin thinking in terms of this procedure or methodology for eliminating divergent or finding convergent series. The remaining slides are all quizzes. There is a quick quiz for 10-4 and 5 together. And this should be 9, 4, and 5. This text that I got this from was a revised vision. Ours is 9, 4 and 9, 5. And then there is a chapter test as well. So I'm going to scroll through these. If you ever want to come back and look at this or try these problems, go for it. And the chapter test solutions. And that's it.